Okay. Physics H, stacks of kinematic curves, worksheet 3. We're going to get a start on this tomorrow and really try to finish a bit of it during first period. Then our lab period, we will try to give a little more experience with these graphs, right? So they make a little more sense. But I'm going to kind of talk through them right now, how you go about doing these, like on worksheet 2 there, stacks of kinematic curves. So we start off given a position versus time graph. So we're given x versus t, and then we are to draw the corresponding v versus t velocity and acceleration versus time graphs. Okay? So the position versus time graph, you usually just keep it in one quadrant, but the velocity and acceleration graphs, we have to deal with positive and negative velocities and acceleration. So let's see here. One of the most basic ones is just a constant increasing position versus time graph, right? So this is something that is increasing in position at a constant rate as a function in time. So as time goes on, the position gets greater. It's linear. So the slope of position versus time is velocity. Gives us the magnitude of velocity. So in the beginning, we have some positive velocity. In the middle, we have some positive velocity. At the end, we have some positive velocity. And that velocity never changes. So for velocity versus time graph, we just have a constant positive velocity. So this one's linear. The velocity is flat. The acceleration, well, if the velocity is constant, now that we know what acceleration is, that means the acceleration must be 0. So if we have a linear position versus time graph, then our velocity versus time graph is flat, and our acceleration versus time graph must just be 0 the whole time. So linear position means a constant velocity. A constant velocity means no acceleration. All right? So you're going to see somewhere we have a negative slope on position versus time. Well, that means that's a negative velocity. If it's a negative velocity, you draw a constant line down here. It's moving in the negative direction. All right? So then the next one we look at is, well, what happens when it accelerates? Well, the position versus time graph ends up being curved. All right? Let me draw the velocity versus time graph here. Now, this is something accelerating in the positive direction because the slope of the position versus time graph is getting more positive, right? We start off with a low slope, basically 0 slope, and as time goes on, the slope of the position versus time graph gets steeper, gets more positive. Therefore, what we have is an increasing an increasing velocity. So this one's curved now. We say linear velocity function, and we see, well, if we kind of pick up this pattern, linear, the next one down must be flat. Meaning, if the slope of velocity versus time is constant, therefore velocity is changing at a constant rate, that must mean we have a constant acceleration. And since it's a positive slope, the slope of velocity is literally the acceleration, and the slope of the velocity versus time graph never changes. So if the slope of the velocity versus time graph never changes, that means our acceleration must never change. It must be positive and constant. So we can kind of use that same wording up here, right? The slope of the position versus time is constantly getting bigger. So the velocity must constantly get bigger. All right?